So this is Fiat Lux II. Good evening, everybody. About a year ago, I gave Fiat Lux to the Liverpool AS. Do you remember those days when we used to meet in person? Okay, this is the sequel to that talk. It doesn't matter if you weren't at the talk a year ago. I'll be recapping the various aspects that are relevant to this particular sequel. For those that aren't very good on Latin, there's Fiat Lux in Hebrew and in Greek, and there it is in English. So this is about the nature of light. Fiat Lux I was a number of demonstrations looking at the nature of light, measuring the speed of light, measuring the wavelength of light, looking at spectral colours and the dispersion of light, and looking at polarization. In this talk, I'm going to be looking at how that understanding of the nature of light allows us to design telescopes. So, nature of light and colours of light have already been covered, and this is essentially how we can use that to think about light travelling through lenses, light bouncing off mirrors, and ultimately the design of telescopes. Now, you might have seen this from the comic XKCD, where it separates telescopes into refractors and reflectors. And as we all know, the main drawback of a refractor is that it might suffer from chromatic aberration, colour fringing if you prefer, colour aberration. And we all know that the main drawback of a reflector is the fact that we are looking at a reflection in a mirror, and therefore we can't see space vampires. That's clearly how we can separate telescopes. So you could think of Fiat Lux II as being Fiat Lux Episode 2, The Vampire Strikes Back. So let's start by thinking about colours and then move on to thinking about other aspects of the nature of light. So in the original talk, Fiat Lux, we saw that when light passes through glass, different colours, different wavelengths in other words, are refracted through different angles. This has been known for a long time, way back to the days of, well, Pink Floyd basically, if you look at this picture here. So that means that any optical instrument, whether it be a telescope or a microscope, anything made using glass lenses will suffer from colour aberration or chromatic aberration, sometimes called colour fringing. And that's essentially inevitable. So if we look at what's actually going on when light hits a lens, if we think of a lens as being a collection of prisms, we can see that in the extreme part of the lens we can think of it as a triangular prism, but the other sections of the lens are behaving in pretty much the same way. As the light comes through the glass, we find that the angle through which the glass is refracted, the angle through which it's bent, will depend on the wavelength. This is called dispersion. Different wavelengths, different colours behave differently in a given piece of glass. And so we can see in this particular case that red, green and blue, I'm just taking those three colours out of the total spectrum, those three colours will end up being focused to different points on the axis of the lens. So we can see red comes to a focus at a particular distance, and green comes to a focus at a different point, and blue comes to a focus at a different point. In effect, the focal length of the lens depends on which colour you're talking about. You can't specify definitively the focal length because it depends on the wavelength. So you have a problem. If you're going to use a lens, you end up with colour fringing. And what it looks like, I'll show a number of these throughout the talk. This is just a few point sources on the left with no aberration, and what those point sources would look like if we had this particular aberration. So if we had colour aberration, instead of getting a nice pinpoint of a distant object, we would see a little bit of colour fringing, perhaps red on one side and blue on the other side, because not all of the light is coming to focus at the same point. So how do we deal with this? Well, there are two ways to approach the problem of chromatic aberration. One, you fix the problem, i.e. you figure out how to deal with it. Or secondly, you avoid the problem. You just use something else. You don't use lenses. The first approach of fixing the problem with chromatic aberration was not taken too seriously, basically because Newton said that CA, chromatic aberration, is inevitable. It's a side effect of what happens when light travels through glass. You can't have the bending of light without the separation of the colours. You can't have, in other words, refraction without dispersion. So if you want to bend light and actually focus light, you are going to produce rainbows, you are going to produce separation of the colours. And as Newton said that, everybody said, well, Newton is always right, so there is no point in trying to fix the problem because Newton has said that it's inevitable. So the alternative is switch and start using mirrors instead. So the second approach was explored, whilst those astronomers that were using refracting telescopes simply put up with the unwanted colour fringing. And that continued until something like the middle of the 18th century, at which point it was realised that if you start combining lenses, especially lenses of different refractive index, and one example of a pairing would be crown glass and flint glass, they refract light in different ways because they have different refractive index, and they also spread the light in different ways. In other words, the different angles for the different colours is different in crown glass and flint glass. So you can see that red, green and blue light still take different paths through the lens, but the result is, well, we'll have to blow that up a little bit to see what's going on, but I hope you can see that if you make the lenses appropriate curves, depending on their refractive index, you can arrange it so that the red and the blue light arrive at the same point. Okay, that means the green isn't in quite the right place, but at least you've got the two ends of the spectrum sorted out. The red and the blue at least agree where they should be focusing, even if the green is slightly off. And this is called an achromat lens or an achromatic lens. You can go one stage further and say, well, if I can do that by having two lenses which get two wavelengths at the right focus, what if I have three lenses? And indeed, you can go beyond an achromat to a so-called apochromat. And if you have three lenses, again, you can see there, each colour is taking a different route through the glass, but they end up at the same point. They end up all focusing to the same point, red and green and blue. Strictly speaking, it's only those three wavelengths, but if your entire spectrum is focused correctly at one end and the other end and in the middle, then it's probably focused reasonably well throughout the spectrum. So this idea of putting three lenses together was a very good way of combating the dispersion. In principle, you're not getting rid of it, you're just controlling it in a way that allows you to focus the light and essentially eliminate colour fringing. Now, in terms of the materials involved, fluorite is actually a common material that's used. It's the mineral form of calcium fluoride. It's low dispersion glass. Low dispersion means that its refractive index doesn't change much with wavelength. And that means if the red and the green and the blue wavelengths all see a lens with very similar refractive index, they will take very similar paths through the glass, and then it will reduce the amount of colour fringing, the amount of chromatic aberration. Just as an aside, whilst we're talking about fluorite as a good material for making lenses, you might notice that various camera manufacturers make lenses and they have different approaches to how to deal with aberrations in a lens. So for instance, Canon lenses quite often use fluorite lenses to actually minimise the colour fringing. Nikon take a somewhat different approach. They take a different extra low dispersion or so-called ED glass. And one of the reasons that NASA uses Nikon lenses rather than Canon lenses is nothing to do with the quality. Let's not argue about which is better. It's simply that Canon have decided to go with fluorite, and fluorite is a relatively fragile glass by comparison with other types of glass, and NASA chose not to go with Canon simply because they were worried about the amount of vibration that the lenses would suffer from during the launch of a shuttle or any other craft. So whether it be for use in the shuttle or whether it be for use in the International Space Station, they've gone with a different type of lens. So not a comment on quality, just a comment about the type of glass that's used. And in addition to camera manufacturers using lenses with intrinsically low levels of chromatic aberration by choosing extra low dispersion glass, they can also compensate for the aberrations that occur by using lenses that don't have simple surfaces. It's relatively easy to grind a lens with a spherical surface. It's rather difficult to grind so-called aspheric surfaces that are not spherical, but that can allow you to minimize the aberrations. So if we look at high quality telescopes, we see, for instance, on the front it might be labelled here, fluorite apochromat, so this would probably be a triplet. Strictly speaking, you don't need 3 lenses to produce an apochromat. These days apochromat is often used to mean very good colour correction. It doesn't necessarily mean you have 3 lenses bringing red, green and blue into focus. It means it's got the colour fringing under very tight control. Here we see it's explicitly labelled as a triplet achromat. The super doesn't actually mean anything, but the triplet tells us that there are 3 lenses in this particular objective, which gives us very good colour control. Some telescope manufacturers go beyond simply 3 lenses. In principle, each lens you add allows you to deal with certain aberration, but of course each lens you add will absorb some of the light, and so generally most people would stop at 3, but you know, there are some manufacturers who are quite happy to go to quintuplet achromats and have 5 elements to try and keep the aberrations under control. If we look at what's going on in camera lenses rather than in telescopes, we find that a lot of lenses, especially those that have zoom so that we look at different focal lengths, there are a number of pieces of glass there. If we reduce that to a schematic, you can see in this particular case, some of the elements, some of the glass in that lens are made of extra low dispersion glass to minimize the chromatic aberration, and some of those surfaces are distinctly non-spherical, so we have a number of aspheric lenses to try and limit the aberrations. So let's think about another aspect of the nature of light, the fact that we are dealing with waves. Yes, we know we're dealing with waves, we've been talking about different wavelengths, but let's remind ourselves about what happens when waves meet each other. When waves superpose on each other, if the waves line up so that the crests all line up and the troughs all line up, then we get a reinforcement of that wave. As you can see, the top 2 waves are being added together to give you the resultant wave there in this little animation. So if the crest of one lines up with the crest of another, which will happen now, we get a very large result. But if the crest of one lines up with the trough of another, then we get essentially 0 in the result. So we can get cancellation of the waves, or we can get reinforcement of the waves. Of course, if we're bringing a lot of light to a focus, we want to make sure that all the waves arrive such that all the crests arrive at the same time. Otherwise, part of the light will cancel out another part of the light. So regardless of whether we're talking about lenses or reflection from mirrors, we must try and arrange it such that the light waves arrive in phase with all of the crests lined up such that they all reinforce each other rather than cancel each other out. If we don't get that right, then we get essentially a mess. We don't get a nice bright clear image, we get a much fainter image and it's not as well defined. So what does that mean in terms of thinking about how we're going to reflect light off mirrors if we want to get beyond the chromatic aberration of lenses? Well, here I'm going to show how everybody draws an ellipse, and we'll see why shortly. I'm sure all of you have done this at some point during your school days. You take 2 drawing pins, put them in a board, take a length of string, wrap it around the 2 drawing pins, and then put a pen inside the string, and just make sure that the string stays under tension, and then move the pen around. What do you find for the motion of the pen? You find that if you join together all of the dots for where the pen moves, you find that you draw out an ellipse. So there we go. So we're talking about a piece of string here, not a piece of elastic, a piece of string of a given length. And the distance between the 2 drawing pins hasn't changed, which means that the distance from the drawing pin to the pen and then from the pen to the other drawing pin must always be the same. For any dot on the surface of that ellipse, the distance from the pin to the pen to the other pin must always be the same. So that ellipse has a very interesting property as far as the design of telescopes is concerned. Those 2 pin positions are called the foci, one focus and the other focus of that ellipse. And because of what we've said about the length of the string, that means if we think of the distance from one focus to the other focus via a point on the blue ellipse, they all have the same total length. if we go from one focus to the blue ellipse and back to the other focus, it's the same length regardless of where we actually hit that ellipse. All of those black lines are the same total length regardless of where we've hit the blue ellipse. And so if we had a light source at one focus, then the light would be travelling exactly the same distance to arrive at the other focus. So all of the light waves from one point would arrive at the other point. From one focus, they would arrive at the other focus, all in phase with each other. So all of the light's paths that we see there would all arrive in phase, and they would all reinforce each other and give us a nice clear image. So what that means is, if we were to build a mirror into that shape, we wouldn't necessarily use a large fraction of that ellipse. Here I've just shown a mirror on the left hand side. Use that if we have a light source on the right, that looks like an old light source, let's make it a new light source, there we go. A nice energy efficient light source on the right hand side placed at the focus. All of the light that hits the mirror and arrives at the other focus, all of that light will arrive in phase and produce a perfect image. So we're talking hypothetically here. Let's assume that we can manufacture a mirror to a perfect elliptical shape. Let's not worry about manufacturing errors just for the moment. I'm also using the language of a two-dimensional system. In practice it would be three-dimensional, so we would be talking about ellipsoids, but let's just imagine we're just talking about a flat section for the moment. So an elliptical mirror will perfectly take light from a focal point and then produce an image at another focal point. And that's a very valuable use of an ellipse. But of course, taking light from one point and producing an image at another point is not very useful for a telescope unless the light source is a considerable distance away. When we're looking at planets and stars, we're not looking at an object 1 meter away. We're looking at an object a few light years away, or 1,000 light years away, or 1,000,000 light years away. So although we want the image to be down here in front of the mirror, we don't want the other focus to be simply a short distance away. What we want to do is to stretch this ellipse such that the second focus is an infinite distance away. So in other words, we don't want a star on our doorstep, we want to look at a star at an infinite distance. So what we want to do is to do the same thing, take the light from one focus to another focus, but that first focus, the origin of the starlight, needs to be at infinity. So what shape do you get if you take an ellipse like this and you simply separate the two foci? Let's imagine one focus stays where it is, and let's drag the other focus off to infinity. What shape do you get if you take an ellipse and stretch it an infinite amount? Well, that shape has a name. Let's remind ourselves again of our schoolboy conic sections. What did we learn at school? Well, the middle of a circle is a focus. Well, technically it's two foci that happen to be at the same place, because if we squash a circle into an ellipse, then instead of having just one focus, when we separate the second focus and drag it out here, then we find that we get an ellipse, where the two foci, one was where the circle's focus was, and now we've got a second focus out here, and that produces the ellipse shown as this black line. They're separated by a finite distance. What if we continue that idea and take this second focus and drag it until it's an infinite distance to the right? Well, then this ellipse gets stretched more and more and more, and eventually it will become a parabola. So a parabola, one way of thinking of these shapes is simply to say a parabola is the same thing as an ellipse that's been stretched until one of its foci has ended up at infinity. Let's just remind ourselves of what these various shapes look like. If we take, they're called conic sections because if we take a cone with a particular axis vertically, if we slice through that cone horizontally, we get a circle. If we slice through that cone at a jaunty angle, we get an ellipse. If we slice through the cone at an angle that's equal to the angle of the cone itself, then we get a parabola. And if we slice through at a larger angle, then we get a hyperbola. So all of these conic sections, circle, ellipse and parabola and hyperbola, we're going to mention in the context of designing telescopes. But before we leave conic sections, let's just remind ourselves that as well as circles, ellipses, parabola and hyperbola, hyperbola don't get used that much, but you can think of a hyperbola as being a sort of flattened version of the parabola, if you want to think of it that way. And as well as all of these being rather important in terms of the design of telescopes, as an aside, we might also realise that, of course, the curves that define the shapes that are good for mirrors are also the curves that describe orbits around the Sun, where the Sun is at one of the foci that we've been talking about. The reason for that is simply because the maths of shapes that reflect light and the maths of how objects move around the Sun, it's essentially the same type of maths, and it gives us the same conic sections as solutions. So Kepler and Newton, Kepler worked out that the planets go around the Sun in ellipses, and the Sun is at one of those foci. Newton figured out the maths behind it all, and we know that planets follow closed elliptical orbits. But if an object came from a great distance, like fell into the solar system from somewhere a long way away, like the Oort cloud for instance, then an object at that distance will follow an essentially parabolic route through the solar system, a parabolic orbit. It wouldn't be a closed orbit in the same sense as the planetary orbits around the Sun. And if an object comes hurtling into the solar system from outside the solar system and it comes in at speed, then it would come in on a so-called hyperbolic orbit, going even faster than an object that simply fell in from the Oort cloud. So there are these similarities between what we're talking about, the shapes for mirror sections as well as the shapes for orbits. I won't dwell on that too long, but it's an interesting connection between the two. So we've decided that if we take an ellipse which focuses from one point to another point, then if we take one focus to infinity, we get a parabola. So a parabolic mirror is presumably a perfect way of focusing light from infinity. So if we take starlight from a focus at infinity, then the light is essentially parallel. It may still be a finite distance, like a few light years, but on the scale we're talking about, it's essentially an infinite distance, and so the light is arriving at the mirror in parallel lines, hits the mirror, and then comes to what is essentially a perfect focus. And again, the lengths of all of these black lines, starting on the right, hitting the mirror, and then coming to the focus, the length of all of these black lines are exactly the same, so that the light, regardless of where it hits the mirror, will arrive in phase with all of the other light beams. So if a parabola is the correct shape to use for a telescope mirror, why are some telescope mirrors made spherical? Circular in section, but spherical when we think of a three-dimensional object. The answer is simply that they are cheaper and easier to make. For amateur telescope makers, and there might be some amongst you, grinding a spherical mirror is relatively straightforward compared to grinding other shapes. If we take two slabs of glass and put some abrasive in between them, and if we move one slab backwards and forwards relative to the other, when one of two things will happen. Either the surface between them will stay absolutely flat, or depending on how we apply pressure as the thing moves backwards and forwards, we might find that eventually then the movement of one over the other with some abrasive powder between them will produce a spherical curve. Why is it spherical? Well, simply because that's the only pair of shapes that will stay in contact with each other. A concave sphere and a convex sphere, which is what we'll end up with from these two slabs of glass that started off as flat, a concave and convex sphere are the only shapes that will stay in contact with each other as you move them backwards and forwards. In other words, perfectly naturally, these two will want to form a spherical surface. Concave in one case, convex in the other. And the more you grind away, then the deeper the concave and the greater the curvature of the convex surface, hence changing the focal length of the mirror. If you want to make anything other than a spherical shape, then that is more tricky, because those two surfaces will not stay in contact with each other if the surface is not spherical. If you want to try and make a parabola will not stay in contact with itself as you move the two backwards and forwards. So it's more tricky to make a non-spherical shape. There are, of course, large spherical telescopes around. Here's the 500-metre aperture spherical telescope. It is a spherical, well, it looks like a wok, but it is actually a spherical dish here. It's not made as a parabola, because a parabola would focus very nicely, but this thing is fixed, and we don't just want to look at what's immediately overhead. We want to be able to look at what's in other parts of the sky, and for reasons I'll show later, a parabola doesn't work too well as far as that's concerned. Whilst we're here, we notice that this particular telescope is called the 500-metre aperture spherical telescope, and hence has the acronym FAST, 500-metre aperture spherical telescope. They put in spherical because although it's a radio telescope, they decided that a 500-metre aperture radio telescope might not be the best acronym for the telescope that they were designing, for reasons that you can perhaps surmise. So let's think about why spherical mirrors are not the best things to use. We know that a parabola will focus light from infinity. What happens if we try to do the same with a spherical mirror? Well, light from infinity will hit the mirror and come to a focus, but note that light hitting different parts of the mirror will come to a slightly different focal position. In other words, the focal length will depend on where the light hits the mirror. If we get rid of the incoming light, we can see that light from the centre of the mirror comes to focus about here, but light hitting the edges of the mirror come to a slightly shorter focus. This is the problem that the Hubble Space Telescope had to endure before it had its corrective optics. And this will be characteristic not only of mirrors, but also lenses that are made with spherical surfaces will also suffer the same so-called spherical aberration. So you can't find a unique point to put your eyepiece or to put your film or to put your CCD camera to bring all the light to a focus. So with no aberration, you would expect to get nice sharp images, but with so-called spherical aberration, because the sphere of the lens or the sphere of the mirror doesn't bring all the light to the correct focus, you find that most of the light focuses at a point, but unfortunately you get a horrible halo around the point-like object, where maybe 10 or 20% of your light produces this halo, which of course destroys some of the contrast that you would otherwise see in your image. If we have a think of what that might look like, again, if we take a sort of laboratory test, if we had 4 points of light on the left, what they would look like with spherical aberration, most of the light would be concentrated in the middle, but you would then end up with halos around the bright points. And so if you think about what it would look like in this simulation of what we would see of Saturn if we had no aberration, in the bottom right we see what that same image would look like if our optics were suffering from spherical aberration. We see a rather fuzzy looking object. It basically blurs the detail. Why don't we suffer from the same thing? We have lenses in our eyes. Why don't we have the same problem that light hitting different parts of our eye come to different focus? Well, Darwinism being what it is, we have evolved with eyes in which the density of the lens of the eye is a little bit higher in the middle than it is towards the edge. We have a graded refractive index, if you like, and hence if it was the same everywhere, we would expect light hitting the outer part of the eye to come to a focus a little too early. But because that's a lower refractive index than the centre of the lens of the eye, it means that all of the light comes to the focus correctly on the retina for those with normal vision. So we don't have to worry about spherical aberration in the human eye. Isn't evolution wonderful? How can you deal with spherical aberration? Well, it's basically the wrong shape of the lens or the mirror. So either you fix it by changing the shape of your lens or your mirror, but that's rather expensive. A cheaper way of dealing with it is to say, well, the light that's causing us a problem is the light that's coming towards the outer part of the lens. The light going through the middle of the lens is giving a reasonable focus, but the light hitting the outer part of the lens or mirror is a problem. So why don't we introduce an extra aperture and block the light that's coming through the outer part of the lens? And then that gives us a much sharper image. You can see the catch immediately. We are now throwing away quite a lot of the light that was coming through the lens. We're only allowing some of the central part of the lens to let the light through. So yes, it gives us sharper images, but unfortunately it gives us much fainter images because we're not using all of the light being collected by the lens. And this was the solution for the days when it wasn't really possible to eliminate spherical aberration from lenses, and we ended up with telescopes that looked like this. This is Hevelius's telescope. The lens is somewhere at the top here. I'm not sure if it's that or right at the end. These objects here are not lenses. They are simply apertures to try and minimize the amount of light being scattered. Somewhere down here we have an eyepiece, and you can imagine how easy it would be to align this telescope and point it at an object. We have a tiny aperture compared to its focal length to try and minimize the aberrations that would be typical of the time. You would argue that that can't be easy to point at an object, let alone how do you deal with sidereal tracking when your telescope is so many meters long. Hevelius said it was easy to use, whereas Halley said it was useless. I'll leave you to make your own conclusion as to the usefulness of a telescope with an aperture so small compared to its focal length. So if we're going to use mirrors rather than lenses to get around the whole business of aberrations, then what combination of mirrors can we use, and what shape would we have the mirrors to allow us to construct a reflecting telescope? Let's have a look at a few possibilities. If we start with a parabolic mirror, then we're going to be focusing light from infinity very nicely to a focus. But if we wanted to place an eyepiece there, our head would of course block the incoming light. So we need to find a way of placing an eyepiece somewhere where we're not going to block the light. So one option, which is of course one of the very early solutions, Newton himself built a reflector and inserted a flat mirror before the light came to a focus, and that sent the light off sideways, and then you can place an eyepiece just outside the tube, and then your head will not block the incoming light. Yes, the mirror blocks some of the incoming light, but that's not necessarily that big a deal. So with a parabolic main mirror and a secondary mirror which is flat, we get the classic Newtonian telescope. Sticking with the same parabolic mirror, and again bringing light from infinity to a focus, we have another way of dealing with what do we do with the light there, because we've got to get the light out of the middle of the tube there, and we've got to put the light somewhere where we can place an eyepiece so that we can actually use this. Well, Gregory's solution was to say, well, the light is coming to a focus there, but I know exactly how to get light from one focus to another focus. All I need is an ellipse. Remember how we got the parabola in the first place? An elliptical mirror will take the light arriving at one focus and it will push it to another focus. So if we place an elliptical mirror there, then the light comes to a focus, and then we regard that as being the origin of the light for the elliptical mirror, which is going to take it and send it somewhere else. And in this case, in the Gregorian design, we take the light to the other side of the primary mirror, which of course means we need a hole in the primary mirror. That's a small price to pay to now put the light somewhere where we can place an eyepiece or a piece of photographic film, or ultimately, if we wished, a CCD detector. Now, Gregorian telescopes are not that common. They were very popular in their time, but the idea of an elliptical mirror there has been superseded by a different way of getting around the same problem. Again, we have light hitting the parabolic mirror coming to a focus, but instead of letting the light go beyond that focus and hit an elliptical mirror, there is an alternative. I haven't talked about the detail, but just like an elliptical mirror will take light from one source and place it at the other focus, if we have a hyperbolic mirror, I'm not going to prove this to you, but with a hyperbolic mirror, light that was going to come to a focus can now be sent to a second focus. A bit like an ellipse, but instead of catching it after it's focused, we've caught it before it was focused. So a hyperbolic mirror placed before the focus of the prime mirror will send the light again through a hole in the main mirror, and that would be the Cassegrain focus. And there are a number of different examples of how the Cassegrain focus can be used. Lots of modern telescopes use the idea of a Cassegrain focus to give you a relatively long focal length in a relatively short tube. A variation on that is the so-called Schmidt-Cassegrain design, where we still have the same basic idea, but instead of having a parabolic and a hyperbolic mirror, now if we use a spherical mirror, which remember is cheaper, it's not necessarily better, but it is cheaper to make. If we use a spherical mirror, we can do the same thing, but of course we know that we will now suffer from spherical aberration. So rather than make a parabolic mirror to try and deal with that, one solution is to add a correcting piece of glass. It looks like it's a piece of glass that's flat on both sides, but actually it's flat on one side and very slightly curved on the other side by just the right amount to correct for the spherical aberration of the main mirror. So this has the advantage that you get all the advantages of a Cassegrain telescope, a nice long focal length in a relatively short tube, but you don't have to make a parabolic mirror. You can make a much cheaper spherical mirror, and all you need to do is to grind a little thin piece of glass to act as the correction plate. And that produces the sort of telescope that I'm sure you're familiar with. Celestron and Meade make quite a few Schmidt-Cassegrain telescopes of various sizes, from of order 6 inches up to somewhere of order 20 inches. Excuse my old use of units. An alternative way of doing something very similar is to again take a spherical mirror, but instead of having a secondary mirror which is placed in the relevant position, we have a curved corrector plate, and instead of using a particular hyperbolic mirror, then a portion of the corrector plate is silvered to do the same job, if you will. And so that gives us a Maksutov design, and perhaps you've seen these. They tend to be a little bit smaller than Schmidt-Cassegrain telescopes, but that characteristic corrector plate shape being concave, as seen from the outside, identifies it as a Maksutov. If that front element looks flat, it's probably a Schmidt-Cassegrain. If that front element looks concave, it's probably a Maksutov. If the front element looks convex, you're probably looking at a refracting telescope with an objective. So there's various telescope types, as I'm sure you're all aware. Some telescope types use combinations of lenses, and they're called dioptric telescopes. Some telescopes use mirrors, and they're called catoptric telescopes. And of course, in the mirror there, in the overlap of this particular Venn diagram, we have telescopes that are using mirrors as well as corrective pieces of glass, and so we have elements of lenses and mirrors, and these are called catadioptric. A little bit of a mouthful, so a lot of people who own a Schmidt-Cassegrain or a Maksutov telescope often refer to them as a CAT, simply as an abbreviation of catadioptric, meaning elements of glass as well as elements of mirrors. So although a parabolic mirror will focus light from infinity that arrives on the axis of the parabolic mirror, unfortunately any light hitting at an angle will not come to a perfect focus. And this type of aberration is called coma, or sometimes it's called chromatic aberration, but you have to be careful not to confuse that with chromatic aberration, colour aberration. So it's normally called coma to make sure we don't confuse the two. That could, in principle, be demonstrated by firing 4 lasers at a parabolic mirror and seeing the reflections of those laser beams. This is something that I would do in a demonstration if we were still meeting in person. It's a little bit difficult for me to demonstrate here with a mirror and a few lasers. You need a little bit of space to do this, and you need to be able to see the laser beams, so you need to drop the lights so you can see how the laser beams are behaving. But basically the laser beams would come to a perfect focus if they hit the parabolic mirror, as it were, broadside, but if we come in at an angle, then those laser beams will not go to the same point. And I can't demonstrate it in the sense of using lasers on a mirror, but I can show you the effect. So if we had again our 4 stellar points, how would that aberration manifest itself? Well, depending on where you were looking, which corner of the image you were looking in, you would get these sort of comet tails, which is why chromatic aberration, or coma, has the name it has, because instead of getting nice pinpoint-like stars, we will get little comets. Coma can be corrected. You can simply add an extra lens into your optical system, and these would be called coma correctors if their prime objective is to get rid of this particular aberration. But wouldn't it be nice if we didn't have that aberration in the first place, rather than make a parabolic mirror which we know suffers from coma and then have to correct it if we want to get nice pinpoint star images? Wouldn't it be better if we didn't have the aberration in the first place? And one option is not to use a parabolic mirror, but to change to a hyperbolic mirror. Remember, a hyperbola can be thought of as a sort of parabola, but just a little bit flatter. That's one way of thinking about a hyperbola. You do have to make it very carefully, but if you do correctly make your hyperbolic mirror the right shape, it will eliminate the aberration that we're talking about. And one classic example of that is the so-called Ritchie-Creation design that was introduced in the early 20th century. So if we take what we had before, a parabolic mirror, and then the secondary mirror which is hyperbolic, if we change that so that the parabolic mirror is hyperbolic, then we can't necessarily see the difference because the difference is tiny, but it focuses exactly the same way when the light is coming in on axis. But this particular design works even if the light is coming in at a slight angle to the axis. In other words, if we have a wide field of view, the stars will stay as pinpoints even in the corners, which they wouldn't do for a parabolic design. And again, there are lots of Ritchie-Creation design telescopes out there. Perhaps the most well known is the Hubble Space Telescope. Yes, strictly speaking, the hyperbolic mirror was made incorrectly. There was a flaw in the manufacture of the mirror. It is still hyperbolic, it's just not the hyperbola that they wanted. It wasn't the hyperbola that it was designed for. It was a slightly different hyperbola, and that produced the optical problems of the Hubble Space Telescope. But still, it's a Ritchie-Creation design, which is fundamentally better than having a primary mirror which is parabolic. The last really big telescope that used a parabolic mirror was the Hale 200-inch telescope on Palomar Mountain. Now, at the time, Ritchie-Creation design was already established in the 1930s and the 1940s, which is the era in which the 200-inch telescope was built. The Ritchie-Creation design existed. In fact, Ritchie was one of the optical people in the optical workshop who were advising Hale about the mirror. Ritchie said we should go for a hyperbolic mirror. Hale was altogether more conservative and decided to adopt the more tried and tested parabolic mirror design. He didn't think it was worth going out on a limb and trying to make a hyperbolic mirror. Remember, we're talking about 100 or so years ago. The technology was a little bit ropey at the time, and he wanted to play it safe. The limitation of the Hale telescope having a parabolic mirror rather than a hyperbolic mirror did not stop the Hale telescope making very significant advances in astronomy during the, half a century or so that it was one of the largest telescopes in the world. But we can see the effect. Here's a picture of the Horsehead Nebula taken in 1951, a beautiful image. Essentially nothing wrong with that, the stars look beautiful. But if we look at an image taken the following year in 1952, this is a nebula which is a much wider angle. I'm not sure if you've seen the Helix Nebula or the Helix Nebula. The size of this nebula is about half of the size of the full moon. It's huge. It's something like 10 times larger in terms of angular size compared to the Ring Nebula. So it's a very wide-angle object, and here the Hale telescope has photographed this, and everything looks perfectly fine when we look at the stars near the centre of the image. But when we go out and start to look at the stars further towards the corners of the image, we find they are very non-star-like. There's a huge amount of chromatic aberration there because the primary of the Hale telescope is parabolic. Now, that's not necessarily a problem. The Hale telescope was not built to take pretty pictures. It was designed as a scientific research instrument. If you want to take wide-angle images, fine, you put in a coma corrector lens before your film to get rid of this aberration. But most of the time, the Hale telescope was interested in what's going on, not over very large wide fields of view, but what's going on when you have much longer focal lengths, the Cassegrain focal length or the much longer Coude focal length, where you get much higher magnification. They were interested in what's going on in this region, or what's going on in this galaxy, or what does the spectrum of that galaxy look like. They were less concerned with the fact that there was a little bit of aberration in the corners of a wide-angle field of view. But the Hale was possibly the last big telescope that actually had parabolic. For essentially from the middle of last century onwards, big research telescopes have adopted the Ritchey-Chrétien design of using hyperbolic mirrors. Although Ritchey-Chrétien is very popular amongst a lot of different telescopes in the world, some of the very latest telescopes have adopted a rather different approach. They've taken a three-mirror approach. And that can control aberrations in much the same way that if you have chromatic aberration in a lens, then if you have a doublet or a triplet lens, you can control the aberrations and trade off one against the other and effectively compensate for the aberration in this lens with mirrors. Any two mirrors might give you a certain amount of aberration, but by having three mirrors you can play around with the different shapes and reduce the aberrations to a minimum. And here we see that the Large Synoptic Survey Telescope, which is due for completion in a couple of years or so, adopts that particular three-mirror approach. The Large Synoptic Survey Telescope has actually now been renamed the Simonyi Telescope, which in a sense, with all due respect to the person who put the money forward and had the telescope named after him, the Large Synoptic Survey Telescope is a more meaningful name in that it tells you what it's going to do. It's going to do a synoptic survey of the entire sky. So naming a telescope after a person is all very well, and if they've provided some money for the project, that's fantastic, but I still tend to refer to this telescope as the Large Synoptic Survey Telescope simply because that describes its function rather better. And I'm not saying any more about that because I've left that to the third part of the Fiat Lux trilogy. Fiat Lux II describes that particular telescope, how it was designed and what science it's going to produce. That is the third part of the trilogy, which I will leave until another day. And not all telescopes, indeed, use conic sections at all. Although hyperbolic mirrors are very popular these days, that's not the be-all and end-all of mirror design. Until fairly recently, the mathematics that allowed you to determine what is the best shape for a telescope mirror or collection of mirrors to produce the best possible images, those were shapes that were produced by equations that you could solve analytically. You can solve them by scientists or engineers or mathematicians with perhaps some help from computing machines, but effectively people could work out what the best shape was. But now we've moved into an era, so for instance the Cherenkov telescope array is being constructed in the high Andes, and there they're using a mirror design not based on conic sections, which is a perfectly good way of doing it, but they've taken a different approach that I'm not going to dwell on, but they've taken a different approach whereby they've used a computer number cruncher to work out the shape of the mirror that they're going to use, and none of the mirrors are conic sections. So in order to figure out what it's going to do, you have to trust the computer program that you've been using to generate the right shape. And the proof in the pudding, of course, will be you make the mirror and then hopefully it will focus light the way you expect it to. But you can see that we're moving in some respects away from the idea that we can only use conic sections to make mirrors for telescopes. In principle, you don't have to if you have the right codes in your computer to calculate what shape of mirror you're going to make. So back in the talk Fiat Lux, we talked about measuring the wavelength of light. I measured the wavelength of red light and found that it was approximately 700 nanometers. And using a diffraction grating, we can see that the blue end of the spectrum is about half of the wavelength of the red end of the spectrum. So that tells us the wavelengths of visible light run from approximately 400 to 700 nanometers, a nanometer being 1/1000th of a meter. And of course, if we want all the light to come to a focus and all of the light crests to be in the same place at the same time, then we need accuracy in terms of the figure of the mirror to much better than a wavelength of light. So we would need the imperfections on the mirror, the difference between the perfect shape, the perfect figure, and what we actually produce. We would like that to be a small fraction of the wavelength of light, certainly no larger than, let's say, 100 nanometers, and preferably rather smaller than that. And computer-controlled fabrication of telescope optics these days is so precise that mirrors many meters in diameter, up to about 8 meters or so, can be figured and polished to the desired shape, whether that be hyperbolic or elliptical, or in the case of other mirrors, it doesn't have to be a conic section. If you're using a computer to actually fabricate the mirror, it does not have to be a parabola or a hyperbola. You can simply tell the computer what shape you want, and then it guides the grinding and the polishing machine. And this can be done with such precision that the surface deviations, the mountains and troughs in the surface of the shape that you're talking about over a distance of about 8 meters in diameter, those deviations might be no more than 20 or maybe 30 nanometers. And it's difficult to visualize that degree of smoothness. So let's just imagine that we take an 8-meter mirror and we scale it up 1,000,000-fold until it's about the size of the Earth. How big would those little deviations be if we scaled the mirror up until it was the size of the Earth? Well, those mountains and troughs on the surface of the mirror would be of order a few centimeters or so in size. And when you think of centimeters over the scale of the Earth, that gives you a very good impression of just how smooth, how precise these modern mirrors can be. In Fiat Lux, we looked at diffraction. And diffraction and interference sometimes get a little bit confused, but in simple terms, interference is when a couple of waves add together and you think about whether the crests arrive at the same point or whether the crest of one interferes with the trough of another and cancels out, etc. If you've got a very large number of waves interfering with each other, then we call that diffraction. So diffraction is just another word for the interference of a large number of waves. And we found that diffraction will affect the optical resolution of an instrument. So yes, we always want telescopes to have as large an objective as possible, whether that be the size of the lens or the size of the mirror. We want the objective to be large simply to collect more light, but because of diffraction, the size of the mirror, the size of the lens, will affect the amount of detail that we can see. Larger lenses, larger mirrors produce better images because the diffraction effects are less noticeable. And so there are two drivers for making telescopes always bigger. Collect more light to see fainter objects, that's always desirable, to see fainter objects. But if we want to see more detail in more distant objects, then we need larger apertures such that diffraction doesn't get in the way. Larger mirrors will produce less diffraction artifacts. And if we look at how telescopes have changed, here we see a dot representing various key telescopes throughout history. The vertical axis is the aperture of the lens or the mirror on a log scale from centimeters up to 100 meters. And on the horizontal scale, we've got the dates from the first telescope in the early 1600s up to the present day. The color coding, blue tells you that we're dealing with refractors, and the other colours tell us that we're dealing with reflectors. The orange means that the reflector had a metal mirror, effectively just polished metal. The green indicates that there was glass, which was then covered with a reflective coating of metal. And when we get to the really large telescopes in the extreme top right there, we go to red because we can't make telescopes with mirrors bigger than about 10 meters. That's pretty much the largest furnace you can make to make an individual mirror. So for mirrors larger than about 10 meters, they are made in smaller chunks. They are segmented. And we can label some of these key points in history. Perhaps you can figure out what some of these are. The G down in the bottom left-hand corner, the first blue dot. I'm pretty sure you can all figure out that that's Galileo's first telescope. And then we have N for the very first reflecting telescope. And again, I don't think it's any leap of the imagination to realise that that's Newton's first reflecting telescope. Here we have a couple of refractors. The ACH refers to the first achromat, the first time when two elements were put together to minimise chromatic aberration, and apochromats came a few years later with three elements to try and minimise chromatic aberration. Here we have H. I'm not sure if you know what that one is. I'll give you a second to think about that. That's one of Herschel's telescope, the 40-footer, the 40-foot focal length telescope. Here we have L in the middle of the 1800s, one of the largest all-metal mirror telescopes. Again, I'll give you a second or two to think of which one that is. That's the Leviathan of Parsonstown. And then here we have Y, the largest refractor that's ever been put into useful service. That's the 40-inch Yerkes refractor. Just to the right of that, in the early 1900s, we have the first use of a Ritchie-Chrétien telescope. You can see that predates by a few years H here, which is the 200-inch Hale telescope. So although Ritchie-Chrétien hyperbolic mirrors were put into use there, Hale was the last parabolic mirror. And on the right-hand side, you can see a couple of telescopes that I've simply labelled here. The LSST, the Large Synoptic Survey Telescope, now called the Simonyi Telescope, and I'll say more about that in Fiat Lux II. And the monster in the top right there is the European Extremely Large Telescope, made of I don't know how many hundreds of segments to give us a mirror 40 meters in diameter. That is going to be an absolute monster, and these telescopes will be coming online in hopefully a few years. They've all been put back a little bit because of our COVID times, but hopefully still by 2022 we'll be starting to get some first light from these large telescopes. So just to summarise, I've been talking about chromatic aberration and how we can minimise or at least control chromatic aberration by using combinations of lenses in 2s or 3s, in doublets or triplets, to try and give us the best possible image from a refracting telescope. And by looking at the interference of light and realising that we must get light focused such that all of the light waves arrive in phase with each other, so that all of the crests line up, so we get the best possible sharp image, then we realise that the best way of doing that is with elliptical mirrors, or if you stretch an ellipse you get a parabolic mirror. Very good, except for off-axis aberrations, in which case hyperbolic mirrors give slightly better performance. And by thinking about how the resolution of a telescope is limited by diffraction, which depends on the aperture of the lens or the mirror, we realise that if we go for the largest possible mirrors, we get the smallest possible diffraction artifacts, and that gives us the highest resolution, the highest detail that we can see in telescopes. So an understanding of light, an understanding of the way different wavelengths and colours pass through glass, an understanding of interference, an understanding of diffraction, using all of this understanding of the nature of light, we can design telescopes that operate at the limits of what the laws of physics allow, both now and in decades to come. Thank you all very much for listening.